Combinatorics is everybody's favorite 13-letter word for how many ways are there to do something, right? It's the study of counting. So just counting the number of ways to do something. So you've seen some of the basic forms of this. So you've definitely seen problems of this type of the hat, jacket, tie variety, or the meat, cheese, bread variety, where you're just told that you have 3 hats, 4 jackets, and 12 ties, because you're a gentleman, and all gentlemen should have at least 12 ties. So how many different outfits can you make? Well, you just multiply all the different numbers together. Now, my number of choices for hats times my number of choices for jackets times my number of choices for ties. So I have 144 different outfits you can make. On the SAT and the ACT, this is more or less, I would say 60% of the time, the combinatorics question that you get is some variation upon this. And that's really all there is to say about it. If you're presented with several different choices for how to put something together, you just multiply all of your choices together, and that gives you overall number of possibilities. This is the easy case, and we like it. But most of the time, in actual pre-calculus type classes, the questions that you come up against are more along the lines of combinations and permutations, which are familiar to some of you, others maybe not so much. If you haven't seen those 2 words before, they might be, again, a little bit intimidating. But what they refer to is not terribly intimidating at all. And indeed, it's not that different from this idea. So what you use these for is when you have a pool of people or a pool of objects that you're pulling from, and you're trying to pick a certain number of them for a team or a collection or something like that. And you want to know how many different teams, how many different collections you can make. That's what these things are for. So the example, let's say I have 300 orphans.
That's not enough. You should have said Ramsey. You need like at least 350 to buy a nice car.
So, well, that's not what we're doing. We're doing something far more noble. I need to sacrifice 5 of them.
I know.
To the demon lord. And I want to know how many different sacrifices I can make. So the way you do this is not too different than what we did over here. Over here we just realized I have a hat space, a jacket space, and a tie space. And in each space I put the number of choices that I have. We're going to do the same thing here. I've got on my sacrifice truck 5 spots, or on the altar, however you choose to make your personal sacrifices to demon lords.
295 in each spot.
So, well,
300.
No,
And then 299,
296.
and then 296.
Yep.
Did you even take finite?
So that's exactly right. When I'm choosing who to fill up my first spot, I've got 300 choices. But once I've chosen them, now I've got 299 choices for who to fill the second spot, and to 298, 297, 296. So I just fill in my number of slots with my decreasing number of choices as I'm slowly pulling crying orphans out of their orphanage. And then, just like here, all I have to do is multiply together all of my choices. So, what this number gives me is what's called a permutation for the situation.
Could also be like 300p5. That makes sense.
Uh-huh. Now, permutation is the number that I'm interested in. There you go. Is the number I'm interested in if order matters. And what I mean by that is you can usually tell if you're dealing with a permutation type problem if each different position has a special title or a special rank, something like that, something to distinguish the different positions from each other. So for example, if the first person that I select is the queen of the sacrificial orphans, and the next one's the vice president of the sacrificial orphans, and this is the treasurer of the sacrificial orphans, if each position is different, then it's called a permutation, and this is the number that we just straight up use. 300 times 299 times 298 times 297 times 296. So permutations, if you have just a random problem, you can usually tell it's a permutation by their titles for the spaces you're filling. President, vice president, things like that. Or there are ranks. So if you see, we're in the Olympics and 12 people are running and we need to choose a first, second, and a third, well, there's our ranks, first, second, third. It's different if Germany wins first and Argentina wins something that's not first. That's different than some other combination that doesn't exist. So we have to keep in mind all of those different considerations. So yeah, you're looking at titles, you're looking at ranks, and you're looking at ordering mattering. So if you're arranging books on a bookshelf, for instance, or you're arranging a playlist, right? For most people on their playlist, order matters because you don't want to have like this beautiful song followed by, the chicken dance or something. You want a good sort of flow between things.
At least 3 songs between the beautiful one and the chicken dance.
Yes, exactly. You want to slowly evolve it.
Or default.
Or default. No, that's an evolution. So if you see that different orders mean different things to you, then it's a permutation type problem. So in those cases, this is what you would do. However, for us, if you don't care about the order, if every position's just like any other, if we're effectively just throwing these orphans into a sack and tossing it on the demon's plate, right? There's no special position in the sack, right? You can't be first position in a sack. You're just in a sack.
Then you would throw them all at once, right?
Yeah, you would just
Otherwise
toss
it'd
them
be
all.
like sack number 1.
Right. No, you're just putting all of them in a sack.
And then
No,
all
you're
of them in a
also-
bigger sack.
Well, that would be cruel. 'Cause
Well, if they were all, then it'd be one big sack and there wouldn't be any order.
oh, well, there you go. So we're putting our 5 dudes in a sack, throwing the sack to the demon. There's no particular position in the sack. Okay. So if you're doing it that way, it's a combination, not a permutation. If order does not matter, if position does not matter, it's a combination. And it has the same start. You start the same way, but what you're going to do is take this guy and divide by the number of ways to rearrange 5 things. Right? Because if, Kevin, Emma, Sammy, Kylie, Lauren is the same offering as Lauren, Kylie, Sammy, Emma, Kevin, right? If that's the same offering, if it doesn't matter, then I have to divide out by the number of ways there is to rearrange you 5 guys. Right? So I have to divide out because we're saying all of those different ways of rearranging you count as one way. It's just that one sack.
Is this the MPR?
Yep. So this is how conceptually to think about it. Conceptually it makes a lot of just plain sense. To get the combinations, you just take the permutation and divide out by the number of ways to rearrange any 5-member group. So that all of those ways just count as one, basically. Now, we have big fancy ways of writing these, which look super cool on a paper and make people think you're important. So how we would write this permutation if each position was different. If this was first sacrifice, second sacrifice, treasure sacrifice, and so on. If each position were important, if order mattered, we would call it a permutation, and the way we would write it is 300p5. So on your calculators, you have a permutation button. On the 84, it requires you to do 300, then use NPR, and then 5.
Where's that button?
300 NPR. On the 89, if I recall, you do the NPR button, and then you would do 300, 5. And on that one, it's under one of your subcategories, and I think it just has little boxes for you to fill in.
Okay.
That's usually how it works.
You just type it in.
But what that equals in terms of,
Really big number.
yeah, it's huge. So you get 2.35 times 10 to the 12th, is it?
Yep.
No permutations. Yeah, 300 NPR.
Big number. Lots of different ways to keep the demon satisfied. So the way that we write this in factorial notation, for those of you who remember what your factorials look like.
Explanation, right?
Yep. So remember, just recall that like 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Remember that notation? That when I use an exclamation mark, it just means start at this number and multiply by everything down to 1. Don't go down to 0 or else your answer will always be 0. Stop at 1 and life will be okay. So,
Couldn't it stop at 2?
I guess you could, but wouldn't you feel bad? One's such an important number. But yes, I suppose if you're one of those people, you could.
I was just asking.
So, if you wanted to do this with factorials, you just take n factorial, the size of the group you're choosing from, and divide by n minus r factorial, so the size of the group minus the number that you're picking
So much more.
out of it. So, yes, but it's how your elders did it. So by gum, you'll learn it too. So that's for a permutation. For a combination, well, you just use the NCR button. And in factorial speak, it's the permutation divided by the number of ways of rearranging your group.
Still, I don't really understand the exclamation mark thing.
So what this is saying is that if you want to calculate this, and you don't want to just draw out all the lines, this is how you could enter it into your calculator,
Okay.
provided that for some reason you forgot that your NGR button exists.
Okay.
But so like 300, 300p5, you could represent as 300 factorial over 300 minus 5 factorial.
I'm
Okay.
really comfortable actually.
And basically this is 300 times everything down to 1. This is 295 times everything down to 1.
Okay.
So everything's going to cancel out except 300 times 299 times 298 9 times 297 times 296,
Okay.
and then you get the same answer.
Okay.
So this is the sort of mathy-wathy way to do it, but you could also do it just by writing out your number of spaces, but that gets kind of tedious if you have to choose a group of, say, 24.
Right.
Kobe.
So there you have it.
Okay.
Okay, so here you go. A little bit of practice.
I'm assuming the R is right.
So take your own.
3.
So somebody needs 3 kittens for a kitten bread recipe. If
Probably will.
he has procured 24 from the animal shelter, how many different kitten groups can he make? So first of all, is this a permutation or a combination problem?
It's
Combination.
It's a combination problem, right? It doesn't matter, we're just going to mix them into the batter. So it doesn't matter what order we do it.
I think we want the sparrow cat in first.
Huh? So there's no, you're not giving the first one like a luscious romp through the park and then the other one's not. It's all the same, we're just putting them in the batter. So how would we represent this in terms of these guys? Where do the numbers fit in and all that good stuff?
24.
Yep.
Factorial over 24 minus 3.
Uh-huh.
Nice.
Anything else? Since it's a combination,
Oh. Oh yeah.
so with an extra 3
Three.
factorial. Yep. So you could do it this way if you love factorials. Alternately, call it 24C3. And that'll give you the number of different 3 kitten baking options he has. Or she, we don't know who ours is. Okay, so what people get for that? 2024?
That's definitely what we got.
So that's how these guys shape up. The calculations aren't really bad. It's realizing when you've got a permutation versus a combination. That's most of the battle for people. And that's why I'm sort of overemphasizing this sack versus ordered position mentality so that you can see right away what you're dealing with. The one interesting problem that they sometimes do is where I'm trying to form a committee and I've got 2 groups of people that I'm pulling from and I'm pulling a different number from each of those groups to make a central committee. So let's say, for example, we have 50 Finch fanciers and 25 A-list simulation game addicts. They need to form a committee of 4 to represent their shared interests.
Which would be.
Which, I mean, so it's self-explanatory, I shouldn't need to talk about it. But I need 2 people from each group to form this committee.
Is it 50C4 plus 25C2?
Is it? Is it?
Oh, wait.
No.
Oh, I didn't realize.
That's
Oh, no,
it.
no, 50C2 plus 25C2. I wrote it. I think.
Very close.
Oh.
Very close. So I've got got this group.
Finch fancy.
I've got my 50 Finch fanciers. And I've got my A-list simulation game fanciers. And I need to make them into a group. Basically, all you're dividing it into are the parts of it which is for the Finch guys, and the part of that which is for the game guys. Right? So how many ways are there of choosing 2 people from this group? As we said, there's no particular special order, it's just I need 2 dudes. So that's 50C2 ways to choose this group. How many choices do I have for over here? 25C2. And just like the hat, jacket, tie problem, I take my number of choices for this, my number of choices for this, and I just multiply them together. Whenever I have a bunch of different slots, I just multiply the number of choices for each together. So just break it up into 2 sub-problems and multiply the results together. And that'll tell you how you can do it.
I feel like we should add them.
Yeah.
I believe you, but I feel like it just makes sense to add them.
It makes some degree of sort of first glance sort of sense. The idea is, however many, for each one of these guys, I have all of these choices. So, if I had only one choice here, it would be that one choice, and then all of these, so it would be 1 times all of these.
And then isn't it's 1 over that answer, right?
No.
1 over that answer would be a fraction. It would be like 0.00000000,
Oh, never mind.
which is a weird number. But you're getting towards probability. Probability has like where we're doing fractions with these
Okay.
things. So you're getting ahead of yourself. Slow down. Put on the brakes. So we're going to answer the age-old question: how do we expand a plus b to the n? We know what it is when n is 1. It's just a plus b. And some of us might remember what happens when n is 2. It's a squared plus 2ab plus b squared. But beyond that, it starts getting a little bit shaky. So how do we deal? Span for n greater than 2. I hear you plead.
So like,
Well, for those of us that have a TI-89 or a TI Inspire, you have a button called Expand that does this for you.
I don't want your calculator.
For the rest of you, here's how you do it. And it actually ties directly into Combinatorics, which is rather cool. So if you did this back in maybe 8th grade, some of you had this, where you had Pascal's triangle, remember? And on and on and on and on. Where each new row is just constructed from the previous row. So like, I always have a 1, and then this guy is going to be 1 plus 3, and 3 plus 3, and 3 plus 1, and then another 1. Just like that. So Pascal's triangle, what it does is it provides me with the coefficients for this expansion, which is pretty cool. So if I wanted to, do x plus y to the 4th and see what happens when I multiply x plus y times x plus y times x plus y times x plus y. I hope I said that 4 times. And what I want to do, that by hand is a horrendous mess to do that FOIL 4 different times. And you're bound to lose some things along the way. So Pascal's triangle represents a nice little hack on the system whereby I know that the coefficients are going to look like this. I need more room. There we go. Yeah. coefficients are going to look like, and then to know what the powers are going to be, I'm going to start with the first one at full power, and then he's just going to drop by 1 each time until he disappears. And then I'm going to, on the other side, I'm going to start with the second guy at full power, and he's going to drop by 1 backwards until he disappears. So if you were to take x plus y times x plus y times x plus y times x plus y, multiply all that out, combine like terms, at the end of the day you would get this thing that we just got in about 15 seconds. X to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. Granted,
Or maybe.
huh?
Do I use the
Expand
expand
button.
button?
You use the expand button.
And it gives you that?
It'll give you exactly that.
Why?
Awesome, okay.
This is a nice little way to do it if you don't happen to have that expand button. This is a nice way to do it, but it gets a little bit annoying if I say needed to do x plus y to the 23rd. I don't want to write Pascal's triangle down to the 23rd level. You could, sure. You could also just multiply x plus y by itself 23 times. And then tomorrow, by the time that you're done doing that, you'll have an answer. So what we then realize, rather sneakily, is that all of these numbers are just combinations. If I'm on the 5th row, they are all just 5c and then their place. So what I can do is I can sort of hop a shortcut here, and instead of writing out the entire Pascal's triangle, if I just want to say no one term of an expansion, I can use my combinations to hop right to my coefficients. So let's say I wanted to know what the third term is in x plus y to the 22nd. If I expanded that guy out, what would the third term look like? Just like here, what's the third term look like? So what you can do is expand it. It might take it a little bit, not too long. That's fine. Look at what the third term is. If it were like the 17th term, it might be a little annoying counting spaces, but it's not terribly inconvenient. But for the rest of us, what we're going to do is realize, okay, there's a coefficient part, an x part, and a y part. So the x part, if we were starting at 22, the third term is going to be 22, 21, 20. The y starts at 0 and goes 0, 1, 2. But then our coefficient for the third term is, we're going to take 22 is our n value, c, and then the third term is going to match this guy. So
Wow.
the way to do it is I'm going to start here. That's my expansion number. This is my term number minus 1. And I'm also going to put that here. And then this guy is just 1 minus 2. So I can hop straight to the term that I want, which is rather nice, and which prevents me from having to expand Pascal's triangle out to 22 rows. So for example, if I wanted the, let's say, 51st term of x plus y to the 112, that even that would be rather inconvenient on even an Nspire or a TI-89. You could use your expand button, but then you've got this screen filled with 112 terms and you've got to go through and count the 51st. Not the best way to spend a Saturday morning. But for us, all you got to do is say 112 C50, y to the 50, x to the 62. And you're done.
That's it.
Yep. So you just take your power there, one less than that goes there, also goes there, subtract those two, that goes there. So, stop murdering my students with bunnies. So it's really easy. As long as you keep to that pattern, you can figure out any term you want. And what's more, this binomial expansion ability is going to come in ridiculously useful in probability later on. The probability that we're going to be looking at, you can get really crazy with probability. You can take years worth of courses in probability and just scratch the surface. We're going to be just scratching the surface of the surface, but that's all that this course covers, unfortunately. Of course, probability was sort of an underrated branch of mathematics for a long time, from its earliest developments in sort of the 17th century. But then once we discovered that it sort of lies at the heart of quantum mechanics, which lies at the heart of all of physical reality, now it has a little bit more respect. So if you wanted to really go into it, you could really do some cool things in terms of figuring out how the world works on a quantum level. We're not going to be looking at that today. We're just going to be looking at normal old probability, rolling dice, and picking cards, and all that kind of good stuff. So, I'm going to remind you just what probability is. Probability is measured on a scale from 0 to 1 about how likely a particular outcome for an event is going to be. Closer to 1, the more likely the event. Nothing too shocking there. If you multiply the number by 100, you get a percent that you're probably more comfortable with. So if you get a probability of 0.85, it means there's about an 85% chance for that outcome to occur. So standard probability, or normal everyday probability, is that the probability of an outcome is the number of ways for the outcome to happen. So, the probability of a particular outcome, as you know, is the number of ways for that outcome to happen over the total number of ways for the event to occur. So, another way to think about it is what you want over what might happen. What you got. The desired outcomes over the possible outcomes. So these sorts of ones are relatively normal. Let's say that you've got a D20. So a D20 is a 20-sided dice used in role-playing with the numbers 1 through 20 on it. So the probability of rolling an even number on a D20 is the number of even numbers divided by 20. Right? There are 20 total different numbers that I could come out with. I'll just divide into that the number of evens. And of course there's 10 evens.
How are you?
So I get a 0.5 probability of rolling an even on a D20. The probability of rolling a number greater than 16. Well, again, there's 4 numbers greater than 16 on a D20. 17, 18, 19, 20. And there's still 20 possible outcomes, so it's 1/5 or 0.2.
Wow.
Pretty simple stuff. Number of ways for it to come out the way you want, divided by the number of total possible outcomes. Now, what happens is that's the probability for a single outcome. What if I ask about the probability for multiple outcomes? Or what if I ask about a compound probability? So for example, what if I say, what's the probability of getting a number greater than 10 or an even number? This is a compound probability because I'm looking at two different types of outcomes, and I'm interested in both of them. So when I see this or, there's a particular way I go about dealing with it. And that's that I can break up this into the probability of getting a number greater than 10 plus the probability of getting an even number, and then subtracting off the intersection of those two outcomes. The probability of getting an even number greater than 10. Right? I've got to do that subtraction, otherwise I'm going to count some numbers twice. Right? Like the number 12 is both greater than 10 and an even number. It's here, and it's also here. So to avoid counting that outcome twice, I'm subtracting off anything that's in the intersection of those two groups. So the probability of getting a number greater than 10 is 10 out of 20. The probability of getting an even number is 10 out of 20. And the number of even numbers greater than 10, there's 5 of them. 12, 14, 16, 18, 20. So I get a 75% chance of that happening. So that's a lovely little formula, but it's very self-explanatory. Right? If I want to know the way for this event, this or this to happen, I got to add them up and subtract the overlap. That's all that it says. It just looks longer and has weird notation. Add them up, subtract the overlap. Now,
Whoa there.
what if I have, instead of asking about several different possible outcomes for an event, what if I ask about an event that gets repeated?
So you roll it multiple times?
Yeah, I roll it multiple times, stuff like that. Well, first I have to establish if each repetition has an impact on the next event. That's my big question.
With the dice, it should.
Right, with the dice it shouldn't. Whatever if I get a 5 now, I have an equal chance of getting each number the next time. Right? Unless it goes through some catastrophic event. But other things will impact. So if the answer to that question is yes, each repetition has an effect on the next event, then we say those are dependent. Occurrences. If not,
Then
they're independent. deal with them separately. Now, this can get very weird. We'll deal with some of that weirdness when we deal with branching probability. But for our intents and purposes, really all that this boils down to is usually they just have you repeating the same type of event. And all that we ask in terms of dependent versus independent is usually replacement issues. So that's usually as far as it goes, which is sort of the smallest case that you can talk about. So for us, it comes down to the sock drawer problem. So we're going to do a little bit of a variation on the sock drawer problem. So this is just what's objectively in the drawer. And what we're going to do is we're going to start pulling objects out. So it all comes down to if replacement occurs or not. So if replacement occurs, what I do is I take my thingy out, I look at it, and I put it back in the drawer. If replacement does not occur, I take my thingy out, and I do what feed it to the dragon, whatever I need to do, and I put it off to the side. I do not put it back in the drawer. So if replacement occurs, or in other words, I put the thingy back in the drawer. And what that means is that basically the probability resets every time. That
Like rolling a dice.
it's like rolling a dice, right? This means that I have not impacted my next pull. I'm not messing with future events. But if there's no replacement, then I am messing with new future events because I'm pulling things out of the possibility for the next time that I pull something out. If I pull out a Jesuit, I now only have 2 Jesuits in there, so my probability of getting a Jesuit again is much lower. So I do impact the future event. So,
Religious person, right?
in order to not write the word replacement every single time, I'm just going to say NR when I mean no replacement and R when I mean replacement. So what's the probability
Oh my god, you're so lucky.
that if I allow replacement, that I get a vampire,
I saw one on
The vampire bites and goes to
then
vampire orphans.
a puppy?
Daily.
So whenever I see the word then, it's going to be multiplying the individual probabilities. When I see or, it usually means add. When I see then or and, it usually means multiply. So this is my key word that I'm going to be looking for to usually key me into the fact that I'm doing multiply-y type stuff rather than add-y type stuff. So what's the probability that if replacement occurs, I get a vampire then a puppy? Well, what's my probability of pulling out a vampire the first time?
6 out of 19.
6 out of 19. Times, I replace the vampire, I put the vampire back in, so now what's the probability of getting a puppy?
10 out of 19.
10 out of 19. So my probability of having exactly this outcome occur, vampire then puppy with replacement, is 60 out of 19 squared. But let's say now that replacement does not occur. No replacement, and I want a vampire then a puppy.
6 out of 19, and then 10 out of 18.
6 out of 19. Yep, same first number, because when we start, it's the same drawer for both. But then,
10 10.
I've got still 10 orphan puppies, but there's only 18 objects in the box because I put my vampire off to the side, leaving 18 things behind. That's how that works. But let's say that I had, what's the probability if I do no replacement of me getting vampire, then another vampire? What would that look like?
No, so then it would be 6 over 19
Yep.
times 5 over 18.
Yep. Exactly. So just keep in mind for those non-replacement events, if I'm doing the same thing, I will keep bringing that top number down too, if I'm bringing the same guy out. Now, I want to introduce you to a somewhat shocking idea, and that is that what if I don't put this little order word in here? What if I don't care about getting a vampire then a puppy? What if I just want to have, at the end of the day, pulled out a puppy and a vampire, but I don't care what order I did it in?
Or when Lord Davenport or whatever it was. Yeah.
I'm going to show you a legit way to do it, and then a cheap but elegant way to do it. Well, this is where branching probability comes in, which is, again, it's sort of like Pascal's triangle, where it's a really nice dodge. It works really well, but it can be physically kind of a little bit tedious. But let's see how that works. So let's say that we want 2 Jesuits and a puppy. I don't care what order I get the 2 Jesuits and a puppy in, I just want 2 Jesuits and a puppy at the end of the day. Well, the problem with doing this is that this assumes a particular order, right? This assumes I'm going to do this and then this. When I don't assume a particular order, it opens things up a bit. So what I'm going to do is make a branch chart for my events. So I've got vampires, Jesuits, and puppies.
And vampire puppies.
For my first choice, so I got a 6 out of 19 chance of this. I got a 3 out of 19 chance of this.
I reloaded this.
And I got a 10 out of 19 chance of this. Then for my second choice, branch, 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 branch. I could get a vampire, a Jesuit, or a puppy, a vampire, a Jesuit, or a puppy, a vampire, a Jesuit, or a puppy. At this point, I've only got 18 things left. I've already gotten a vampire, so this will be 5 out of 18, 3 out of 18, and 10 out of 18. Chance there.
And that's also right at 18, right?
Yeah, all these are going to be out of 18. Here, if I got a Jesuit my first turn, then I still had those 6 vampires, but now I'll be down to 2 Jesuits.
Is this the best way of doing this? Like just writing it
No.
out?
But it's the only way of doing it. You have to be a little bit clever to do the other way that I'm going to show you.
Oh, the elegant, cheap way?
The elegant, cheap way requires you to be a little bit comfy with your own fabulousness. So if you're not comfortable in your fabulousness, it might be more difficult.
Kinda hard
So
when you're this fabulous.
just reflect on that for a while. Here I've already gotten the puppies, now I'm down to 9 puppies. But that's not it, because I'm interested in 3 objects, so now off of each one of these, I've got to draw 3 possibilities. So again, vampire Jesuit puppy, vampire Jesuit puppy, vampire Jesuit puppy. That'd be a good band name, actually. Vampire Jesuit puppy. Vampire Jesuit puppy, Vampire Jesuit puppy. Vampire Jesuit puppy.
Vampire Jesuit.
Vampire Jesuit
No,
puppy.
no orphan though. That makes it too long. Right?
No.
Puppy.
That
And then
it wouldn't
maybe
fit
like,
on the
I
list.
think just
I think
vampire
Jesuits should
orphan
go
puppies
first.
would be better.
So,
Vampire orphan.
but then we're leaving out the Jesuits.
I think that's my favorite part.
So, you'll notice I didn't write the probabilities down on all of these because, thank you, Wolfgang. Because I'm only interested in branches that have 2 Jesuits and 1 puppy in them.
Okay.
So I'm not going to write the probabilities on all of them until I find which ones I want. So I want 2 Jesuits and a puppy. I don't want any vampires, so I don't care about any of this stuff.
Can you just erase it? That'd be too much.
So I want 2 Jesuits and a puppy though, so that could be Jesuit, puppy. That one works.
Puppy, Jesuit.
Jesuit, puppy, Jesuit works.
Oh my god.
So those 2 work.
And then the puppy one.
And then I've got the puppy one. So I can go puppy, and then I have to go Jesuit, and then I have to go Jesuit again.
Oh, that's the only.
So those are the only ones which give me 2 Jesuits and a puppy. Or this branch, and this branch.
So will it always be like 3 branches then? Because it's 2 Jesuits, 1 puppy?
If I'm just picking 3 things, if I'm picking 4. So here, if I'm looking Jesuit, puppy, this is 10 out of 17, right? Because I haven't picked any puppies yet. If I go Jesuit, puppy, Jesuit,
She would want Ramsey in there.
that branch is 2 out of 17. If I go puppy, Jesuit, 10. I've already picked 1 Jesuit, so now I'm down to 2. So this is 2 out of 17. So,
Ramsey.
at the very end of the day,
10 out of 2 out of 6.
it's the probability of this outcome plus the probability of this outcome plus the probability of this outcome. But what you'll notice is that these 3 are all the same number. Right? I got 3 times 2 times 10, 3 times 2 times 10, 3 times 2 times 10, and 19, 18, 17. So it's just 3 times. You would multiply all that together and get your answer. But what I want you to see is that I could have skipped this entire thing.
Oh, thank the Lord.
Oh my god.
But you had to be sneaky.
Make it.
So-
Jesuits.
So the bottom
Is the Pope a Jesuit?
is going to be probably not.
As he started saying that. Didn't get the default.
So the bottom is going to be just, I notice I'm pulling 3 objects out of a group of 19. So it's just start at 19 and multiply down by 3. So the bottom is just 19p3. Or just think about it as I have 19 objects, I'm going to keep multiplying down until I've got the number of things I'm interested in. So I'm interested in 3 things, so I'll multiply down 3 times. Next, for the top part, all I've got to do is start with how many of each of these I have and multiply down the number that I want. So for example, I want 2 Jesuits, so I'm going to start at 3 and multiply down twice. And then I have 10 puppies, and I only want 1 puppy, so I only multiply down once, I just leave it. And then this one, to get the number out front, it's the number of ways of rearranging these things. So that there is just the number of ways of rearranging 2 Jesuits and a puppy. Right? In other words, it's the number of ways of JJP, it's the number of ways of rearranging that. So there's 3 different ways I can rearrange that. It's either JJP, it's JPJ, or it's PJJ.
PJ is J.
So 3 ways of rearranging that. So if I don't want to do this gigantic chart, if I don't want to deal with the branching,
Can we try one with 2 Jesuits, 2 puppies? Like make one like that.
yeah, we can make one. Well, we're gonna here.
So it'd be 4.
We can just
No, it'd be bigger than 4.
cheat a little bit. So again, I'm going to remind you there were 6 vamps, 3 Jesuits, and 10 puppies. And we're going to see what's the probability of getting 2 puppies. Now let's do one of each. Let's do, what's the probability of getting a vamp, a Jesuit, and a puppy? One of each.
Would I start with the big 3?
So, well, how many different ways can I write this?
67. I guess more than 3 times.
And then who have I not put up in the front?
9.
P.
Is it 9? I'll get 7, 6.
So there's 6 different ways of rearranging V, J, and P.
Is there an easier way to find it instead of listing it all?
Yes.
How would you
Yeah, there is. The way that you do it,
No.
think of it as a word, is, let's say it were V, J, 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 P, V, something like that. So the number of ways of rearranging that are going to be the number of letters factorial.
3. Oh,
So 6.
9.
So this is the number of letters on top. And then I'm just going to divide by the repeats. So I've got a 3 repeat there, and a 2 repeat for the V's.
So in this case, would it just be 3 factorial?
So in this case, it would be 3 factorial, which is 6.
Or is it- okay.
Exactly.
Because it's
So this is going to be 6 times, on the top, I want 1 vampire, 6, I only want 1, so I don't need to multiply down any. I want 1 Jesuit, 3, I want 1 puppy, 10, and I have 19 total objects, of which I'm picking out 3,
Oh my
so 19 times 18 times 17. So,
Where's my shoe?
so this makes it really fast
Hey, it was an even
to deal with that relatively complex situation. I just take my number of ways of rearranging that amount of things, multiply by how many of each I have, counting down the number that I want, and dividing by the total number of things, again, counting down. So what I could theoretically do is what's the probability of getting 2 vamps, 2 Jesuits, and 3 puppies after I pick 7 things? If I were to do this through the branching method, I would have 3 to the 7th branches to deal with. That is a few.
2,187.
2,187? So yes, by the end I'd have 2,187 branches to deal with, which is more than we want to deal with.
Are they gonna have that on the final?
This
All the
particular...
branches?
Oh, no. They'll, if they do anything, it'll be like 2, maybe 3. But, yeah.
Okay.
But
let's do
we, because we're awesome, can deal with this.
it. Yeah.
So this is 7 letters. I've got 2 repeated V's, 2 repeated J's, 3 repeated P's. And then my vamps start at 6 and go down. I want 2 of them. My Jesuits start at 3 and go down. And I want 3 puppies. So 10 times 9 times 8. These are my puppies. These are my Jesuits. These are my vamps. And I've got 19. And I want to count down till I get 7 of them. So I can either draw 2,187 or whatever it was branches, find all the different branches that pertain to what I want, and then multiply them and add together all the results, or I can just do this. But as I say, you have to be a little bit clever. You have to remember how to figure out all the different ways to combine those possibilities, and you have to remember to count down each set of numbers. This way of thinking about it, as far as I know, isn't actually in any high school textbook, which is dumb. It's they have you do it like this, and it's terrible of them, because with just a little bit of thought, you can see these patterns show up, and once you see the patterns, this goes away, and you can just deal with it like rational people.
They don't want to teach us a shortcut.
Well, I mean, the shortcut comes from just using your reason on this, and just saying, that's the same number, and that's the same number, the number of ways that I can rearrange those letters. I bet I could shortcut this whole process. So that's your way of shortcutting the whole process, and it's really quite neat. Okay, so the last thing to cover is binomial probability. And luckily it's super simple. It's like super simple. It is, but it only pertains to one sort of case. And that case is that I have a repeated event where each event does not impact the next. So repeated event. Each trial doesn't impact the last, or the next rather. I have to know the probabilities of success and failure.
Like the probability that I pass is 5 nothing.
For example, I don't know that, but
We can all guess. 0.
and that's pretty much it. And what binomial probability will let me do is it will let me figure out what's the probability of getting a certain number of successes in a certain number of trials. So I have to have it be a repeated event where each event does not impact the next, and I have to know what the probability of success or failure is in each given trial. So, for example, let's say that we are, I don't know, shooting womp rats back home.
And I bet exhaust ports don't even run as fast as womp
No,
rats.
I bet not. We have an 80% chance of hitting. And a 20% chance of missing. So my question is, if I fire at 20 womp rats, what's the probability that I hit 12 of them? Okay. So this is under my average. If I fire at 20, I should be hitting 80% of them. I should be hitting 16. So this should not be terribly probable, but it's possible. What this just is it's basically just a question of finding this event's position on Pascal's triangle. Probability has to do with Pascal's triangle. So this is actually a Pascal thing. So the way for me to figure out what that probability is I'm going to take, so the coefficient, remember, runs off of combinations.
You're not getting it back.
So I've got 20 romp rats, and I want to hit 12 of them. So the probability of that happening is 20C12 times my probability of hitting, 0.8, to the number I want to hit, times my probability of failing, that's a big 2, probability of failing, times the number of times that I must have failed. If I multiply those numbers together,
Where's the 8 from?
0.8, oh, well, if I hit 12 times, I must have missed 8
Oh, gotcha.
if I'm firing 20. So generally speaking, the probability of n successes, let's say r successes, in n tries is going to be NCR, your success probability to the r, times your fail probability to the n minus r. That's it. If I have a situation that fits the binomial criteria, repeated events of known success probability, then I can do this. I can just say, instead of doing, again, a huge branching chart to figure out what happens, I can just say, all right, it's my chance of success to the number of successes I want, my chance of failure to the number of failures I want, all multiplied by NCR. So as long as you keep to that idea, the hard part is really just recognizing that it is a binomial problem. So you can always recognize a binomial problem by, it's usually, what's the probability that out of this many tries, I get this many results, either successes or failures, or I have this many children, what's the probability that I have 14 boys, something like that.
Wow. Wow.